All right, hell yeah. So we have material mechanics. Now this took me like all day to get. You know, some problems you try and then you're like, shoot, I'm not even getting the answer in the back of the book. So and the answer in the back of the book, what the hell is that? It says that this X value is 135 millimeters. So we're going to break down this problem because it involves springs, and for the love of God, it involves two springs, and it just tricked me out. I'm going to get right to the point. What tricked me out is, as the picture shows, let's say this had no weight. You know what I mean? This was a weightless bar, and so I just thought both springs were hanging down to the same location. But now, you know what I mean? And that's just shame on me. I really don't read problems. So the length of this spring at rest, its natural length, is 250 millimeters, and the natural length of this one is 200 millimeters. And they mounted this one at a height of 80 millimeters. So the natural length of this spring wants to be 280, and the natural length of this spring wants to be 250. So I mean, the natural length of this spring should be like down here, and then you'll get 280. Okay, so that was like the first hiccup that I had with this problem. But regardless of that, I think that is a good. So that's where we're going to start. We're actually going to start that problem first. Had they just mounted this at a height of 200 millimeters, so we're just going to say both springs have a natural resting point of the same. And now we're going to include now the weight of this, and the weight of this is 25 newtons. So basically, the weight is going to act right in the middle, and so both sides will have, from the weight of this, they're going to have 12.5 newtons on both sides. Okay, now we can put this force anywhere. See how we can vary it? Now, anytime you get a problem where you're just not superb at going right to, you know what I mean? What do they call it? Coming up with a nice formula exactly for X and how it relates to everything. Because this one gets a little messy, you know what I mean? It's just a lot of variables involved. So the first thing I do is say, screw it. Put P just right here. And then we want to see what's going on. Okay? So P is our load, and it's going to be 18 newtons. So we're just going to add 18 newtons here. And if Px right here, it's going to be 0 newtons over here. Okay, and now from this point, now we just want to know what the hell a spring does. Springs are the simplest thing, but for the love of God, they're so complicated. But at the end of the day, the equation for the force of a spring is, it's this spring constant, which they just give you. And the cool thing about the spring constant, always pay attention to the units. So, newtons per meter. So what this says is if I know I'm putting like 10 pounds, or let's say 10 newtons or whatever, if I'm putting 10 newtons on the spring, you know what I mean, and then it changes its length, well, let's just get to the equation. So the force of a spring is this spring constant times the change in length of the spring. So anytime you get a spring problem, like always figure out what the natural length of the spring is. That's super important. And then see if it changed length. And if we added 10 pounds on it, heck yeah, we get a change in length. And or 10 newtons. So let's do that. Let's do that for this first spring. This first spring has a spring constant. But let's change the spring constant, because the spring constant says it's for every 400 newtons, you're going to get 1 meter. We're only putting 10 on that, so I have no idea. You know what I mean? Let's say we put 400. So for this, for the first spring, the spring constant is 300. So on the first spring, let's say we put 300 newtons. Well, the whole thing's going to move 1 meter. So it's going to have a natural length, and then we go and put we go and put 300 newtons on it. Well, guess what? This spring down here just changed its length by 1 meter. That's kind of what that says. But we want to work in millimeters. It'll just make so much more sense. So we take the spring constant of 300 newton meters, and we'll do this 100%. You know what I mean? So we wanna cancel some units. So we put 1 meter up top and 1,000 millimeters down below. Now we can cancel millimeters. This is your unit conversion. You can change any units to whatever units you want. You just got to be like, well, if I have a meter down here, meter up there, they cancel, and then we get this. So anyway, so it's going to be 300 divided by 1,000. That's moving the decimal place 3 times to the left. 1, 2, 3. So we're going to get K1 is 0.3 newtons per millimeter. So now, heck yeah. So for every, so 0.3 newtons per millimeter. So for every 0.3 newtons, I get to move 1 millimeter. That's what that says. So let's say I have 10 newtons. What is it? Isn't that about 30 of these 0.3 newtons? So it's going to move 30 millimeters. And let's do that one, because if we take and so the first thing to do is realize that, hey, if we want to know the change in length, that's what we were trying to figure out, then you just move this equation, you know. The spring, anytime you get like a simple equation that has kind of 3 things going on, well, you can rearrange them. So this just says, hey, the force is equal to the spring constant times the change in length. But I don't know the change in length, maybe. But I do know the force on the spring. I put 10 newtons on it. That's what I'm going to do on a spring. And so we're gonna rearrange. We're gonna bring the K downstairs, and then we'll get change in length. And so we get change in length is equal to the force of the spring divided by K. Cool. And that's going to be the 10 newtons we're going to try on it, and we're going to get 0.3 newtons per millimeter. So now you can see that the newtons cancel. The millimeters is downstairs, but it's divided downstairs, so this pops upstairs. And then we get, and then 10 divided by 0.3, close enough, is 30 millimeters. I think it's like 33.3. 10 divided by 0.3 is 33.3 millimeters. Okay, but now we have an understanding of how springs work. I got to put more time on the clock. All right, heck yeah. Now we're back. Okay, so let's flesh out the spring constants for both these, because this one is 0.3 newtons per millimeter, and now we kind of have an understanding of that. For every 0.3 newtons, you know, 1/3 of a newton, we get 1 millimeter of change. So let's just go down right here. So now, because what you want to do is just kind of get an intuitive feel. Well, you were saying if we take the force in newtons and divide it by the spring constant, millimeters pops upstairs. So let's do that. So if we put this full load over this point right here, we'll get 12.5 plus 18, and then divide it by the spring constant. Cool. So we would get a change of 100. This thing would change, the spring would change length by 101 millimeters if we did that. Well, now let's take the P all the way over here. So now this would be 0, and then this would be 18 newtons. So we'd have 12.5 plus 18, and we're going to divide it by the spring constant. The spring constant over here is 0.4 newtons per millimeter. They give it as 400 newtons per millimeter. Divide by 1,000, that's 0.4 newtons per millimeter. If I said that right, I think you get it. Okay, so this 30, so these add up to 30.5 if we put the load right there. Divide by 0.4, whoa. And we get a change in length of 76.25. Now let's say, because I'm gonna try to solve the problem how I originally thought it looked, because it's the easier of the two, is that we're just going to say, hey, this length right here is 200. We're not even going to worry about this. That's why I didn't read this H value. So we're just going to get rid of that. This length right here is 250. So we're going to mount these springs at their natural length. And if we put the load here, this one's going to change in length of 101. But if we move the load all the way over here, this one's going to change length by 76. Okay, and well, we need a couple values, because if we put the load right here, this one does change by 101, but over here we'd only have 12.5. So we got to go 12.5 divided by that spring constant. So now we're just kind of on a roll, and that would only generate a change in length of 31.25. So these two are related. And if we put the force right here, we already calculated that as a change of 76 millimeters. But then over here would only have 12.5. So 12.5 divided by 0.3, and this would be a change in length of 41.6 millimeters. So now these two are related. So now we have a relationship, and any problem, and what we're doing is we're like, hey, we're just trying to use brute force to actually see if we can find a spot by guessing. Like, we're saying we're going to throw in the towel on trying to find the perfect formula that shows where x is with every value of p and w and h, because that's what we're going to do in the end, and k1 and k2 and l1 and l2, you know what I mean? But we just want to set it up and be like, for the love of God, where should we put this load? And we already showed that if we put the load over this point A, it's going to go down 101, but then over here it's only going to go down 30. So visually it's going to go down 100, and this one's only go 30. Okay, but now let's move the load all the way over here. Now this one's going to go down 76, and this one's only going to go down 41. Oh, okay. Well, that's getting closer. So, yeah. So that's where I kind of got into this problem of just like, oh, okay. And so, and now I have to say a huge, like, hey, my problem that I solved was way different. Because even just that, even just doing that, if I put the load here, it's going to go 100, and if I put the load, and then there's no load over here, it's going to go 30. Well, this one's way saggy. But then if I put the load all the way over here, this one goes down 76, but this one only goes down 41. So they're almost equal. So it seems like, hey, the load should be somewhere right here. You know what I mean? So that, just from that setup, is what we gained from this problem. But I do have to, if I'm going to solve this actual problem that they're laid out, I have to say, hey, if h, okay, so let's go back to their setup, because we don't have 200 millimeters right here. We only have 250 millimeters right here, and we have and it's saying this space is 80. So if we go up to this 250 and then go down 80, all we're left with is 250 minus 80. So 250 minus 80, we're only given 170 millimeters. But the natural length of this spring is 200. So now it's just like this spring is like all bunched up and is probably wanting to put a force this way. You know what I mean? And that's too much for your mind to handle. So you know what I mean. But so that says when we said, hey, this one, if the P was over here, and we're down 100, but we're only down 30. Well, but plus whatever force that was trying to push down, so that might even it out. So that's why the P, final is going to be really close to how it's drawn. And this full length, if you're reading, because I won't read the problem for you, is 350 millimeters. Okay. So the problem in the back of the book, we'll get that this P is exactly 135, right about there, let's say. The problem that I, thought I was doing was if both springs were at their natural length. Okay, so we're going to grab another sheet of paper. And we're going to solve the problem where, hey, both springs are at their natural length, 200 millimeters and 250 millimeters. And we're going to solve that problem by brute force. So we've already put the P here, and it was too much, and then we put the P there, and it was too much. So but I think we need to do that one more time. So we're going to put the load here, and this load is going to be half the weight, so that's 12.5 newtons, plus P is 18. So there you go, plus 18 newtons. And if we do that, 12.5 plus 18, we get 30.5. And again, the force on a spring is K times the change in length. And the change in length is kind of what we're trying to find, because the problem that they say is, hey, we want this bar to be totally horizontal across. And if both springs are at their natural length, then the change in length has to be the same. So when this bar goes down to here, the change in length in this spring is the same as the change in length of that spring. So that was the problem that I was initially solving, and I'm going to say the change in length of 1 is equal to the change in length of 2. Because of the problem they have set up, crunching this spring down kind of makes it too much for my mind to handle. So that is something that I always do, is like, hey, let's solve an easier problem, and then we can go back and see what the trick, you know what I mean, is like, hey, what's the trick here? But yeah, so for this problem, natural lengths, and then the weight of W and wherever we put P, we still have to make these even. This whole bar is going to be perfectly horizontal. That means the change in length of this spring is the same as the change in length of that spring. Cool. All right, so let's do it. And we know that the change in the length, if we move around this equation, bring this downstairs, and bring K downstairs. So change in length is force divided by K. Cool. And the force is this. And then change in length of spring 1 is equal to the force at 1 divided by K at 1. And then the change in length of spring 2 is the force at 2 divided by K2. Cool. All right, so now let's set it up. P is here. We're going to have 12.5 plus 18 divided by the spring constant. K1 is 0.3 newtons per millimeter. K2 is 0.4 newtons per millimeter. Okay, so 0.3, and we get 101.7. 101.6, let's say. Cool, millimeters. And then so we put the load here. There is no load over here, but it still has half the weight. You know what I mean? The weight is all, no matter how this thing's not swinging to the side. So this thing we're just assuming is straight up and down. All right, so we're assuming that whatever, even if it's at an angle, the weight of this is still distributed on both sides. And, well, I guess if it's horizontal, then obviously the weight is distributed on both sides evenly. Okay, so this will still have 12.5 newtons over here. We go 12.5 divided by the spring constant. See, now we're just on a roll, and we get 31.25. So, hey, this number's bigger, this number's smaller. So that's the first thing I do, is like I set up where P is just right here, okay? And this number is too big, this number is too small. So now let's take P right in the middle. That's a good thing to do. And so we're going to, so that means that we're going to have 12.5 from the weight plus 9 newtons, and then over here 12.5 plus 9 newtons. You know what I mean? So that visually that's pretty fast to do. 12.5 divided, so 12.5 plus the 9, 21 divided by the spring constant, 0.3. That gives me 71.6 millimeters. Over here, that same 12.5 plus 9 divided by the spring constant, 0.4. This gives me a change in length of 53.75 millimeters. Okay, hey, look at this. This one's still bigger. Okay, cool. So now we moved halfway. Let's move halfway this way again. So now we're going to put P here, and but now we got to figure out kind of what's going on. This is where you do the moment equation. You know what I mean? Just visually, if I put, so this is what happens with your you know, when the weight is in the middle. If all the weight's in the middle, you're going to have even weights on both sides. You know what I mean? But if I take all the weight and put it here, well, there's going to be no weight over there. We've already kind of established that with this P. If we put P right under this spring, well, this doesn't have to take any more. It takes none of this P. Put P all the way over here. Over here takes none of the P. Okay, so, and then if we do it halfway, it'll take half that load. Half of that 18 newtons, that load P. Cool. All right, so let's say we put it at 3/4. You know, just visually, it's like, hey, this one's going to take more, this one's going to take less. Okay, and so here's the math just quickly. So that this distance is a 3/4, and this distance is 1/4. Okay, so one of these numbers is bigger, one of these numbers is smaller. But don't get that confused, because if we have the load over here, this one's going to be the bigger number. So this distance, it's just bigger, is corresponding to the load right here, because this load is already closer. See how it's closer? This load is very far away from that, so the smaller number comes over here. So basically this load of 18, we would go 18 times, and this is 0.75, this is 0.25. So now we have fractions of the total distance. And why I'm saying L is whatever, you know what I mean. But we want the percent of L. So if I say, hey, this is length L, and then I would say this is 0.5L, 0.5L. It's 50% of L, 50% of L. So it doesn't matter what L is. L is going to be 350 millimeters, but we want to know the fraction of the length. So there you go. So right here is going to take more of the load, so it's going to be 18 times 0.75. Over here is going to take less, it's farther away, it's going to take 0.25 times that 18. So let's calculate those. We got 0.25 times 18, that's 4.5. It still takes half the weight, because like we said, this thing's horizontal, and this is going to still take half the weight. So we take that 4.5 plus 12.5, because this weight is 25 newtons. You know what I mean? Let's do that if you were reading up there. Okay, so we have 17 divided by the spring constant, 0.3, and we get 56.6 millimeters. Okay, now over here we got that 18 times 0.75 divided by, 18 times 0.75 is the load, is the percentage of the load over here plus the half the weight, 12.5, 26 pounds divided by the spring constant, 0.4, and we get 65 millimeters. Cool. Now this one's bigger, and this number's smaller. And this is the cool thing. Let's say, you know, anytime that we were over here and now we're over here, well, hey, now we know that the load needs to be put somewhere in between halfway and 3/4. You know what I mean? So that's cool. When you're just doing brute force or guessing, you put the load over here. We had too much over here, too little over here. Then we put it at the halfway. We still had too much over here, too little deflection over here. The thing's still looking like this. But now we put the load at 3/4, and this one's sagging to 65. This one's only sagging to 56. So I mean, I think we're getting better. And you know, you could do the halfway thing, or you could just guess. So let's go on this one. We're just going to say, hey, if it was at 0.75, well, let's put the load at 0.7 and see where we're at. So we're going to put the load right here, P. This distance is going to be 0.7, this is going to be 0.3. So we still have that, that thing where this is the lower number, this is the bigger number. This P is more under this one, so this number is associated over here, this number is associated over here. So we're going to have, on this side, we're going to have 18 times this 0.3, 18 times 0.3 plus half the weight. Got to remember that. Divided by 0.3, and we get I'll go over here, 59.6 millimeters. And then over here, we're going to have 70%, 0.7 times 18 plus 12.5, divided by the spring constant, 0.4, and we're going to get 62.75 millimeters. Okay, this one's still bigger, so we can even continue on just a little bit more. This number's smaller. So we're still going that way. You know what I mean? And just visually, if you forget, like, oh, which way do we go? It's like, well, if the weight's over here, it's going to sag this one more. Hey, it looks like this one's sagging more. The weight is too far this way, so we need to move the weight back that way. So let's move it to 0.65, because that was 0.7. So if we go 0.65, this one's going to be 0.35. This number is associated with there, 0.65 is associated with there. So let's do this one first. 18 times 0.35 plus 12.5 is half the weight, divided by the spring constant, 0.3. And we get 62.6 millimeters. And if we go over here, 0.65 times 18 plus 12.5 divided by the spring constant, 0.4, is 60.5 millimeters. Okay, now this one's too big. Cool, so even just right here, it looks like we're going to be like 0.73. And I guess we could do that one, 0.73. If we got 0.73 here, we must have 0.32 here. Because 0.73 plus 0.23, no, sorry, 0.2, this would be 0.28. 0.73 plus, no, 0.37. So if we have 0.3 on one side, so it's basically the equation is 1 minus 0.73. 1 minus 0.73 is 0.27. So 73% on one side, 0.27 on the other side. So that means the P is somewhere right here. 73% of the length is over here. 27% of the length is over here. This 27 is associated with this side. This 73 over here. So let's do that. 0.27 times 18 plus 12.5 divided by 0.3. So we get 57.86 millimeters. And then over here we're going to get 0.27. I'm sorry, 0.73. 0.73 times 18 plus 12.5 divided by 0.4, and we get 64.1 millimeters. Oh, so that didn't work. So hopefully I didn't make a big mistake. Oh, did I already go to 0.65? Yeah, right here I went to 0.65. And we said we were too far this way. So the number is going to be in between these two. So again, if you come back here to be like, hey, which one was bigger? It's like, well, this one was. It was too far this way, and this is what we were left, 0.65. So now we got to. So this was a mistake, but we just got to move it in between here. So now we're going to go, hey, 0.68. 1 minus 0.68. Let's get some more time on the clock. All right, so we have 1 minus 0.68 is going to be 0.32. So we have 68% of the length over here, 32% of the length over here. P is more over this way, so this one's going to be associated with the 68% of the load. This one's going to be associated with 32%. So let's do this one first. 32% or 0.32 times 18 plus half the weight, 12.5. Divided by the spring constant, and we get 60.86 millimeters. And over here, it's going to be 0.68 times 18 plus that 12.5 divided by the spring constant, 0.4, is 61.85 millimeters. Okay, even here, this number is bigger, so 0.68 was a little bit too far. I mean, we could go 0.67, and, 1 minus 0.67 is 0.33 times 18 plus 12.5 divided by 0.3, and we get 61.46 millimeters. 0.67 times 18 plus 12.5 divided by 0.4 is 61.4 millimeters. So hey, now we're on. So that was the answer. You know what I mean? So using brute force, we're like, heck, we got to put x at 0.67. 60%. This is 0.67 of whatever the length is. That's 67% of whatever length that we chose. You know what I mean? It doesn't really matter what the length is. You know what I mean? So there you go. And the length in this is 350 millimeters. So if we did it like this, we'd have 0.67 times 350, and we would put x at 234.5 millimeters. So that is the problem that I initially started, and I couldn't figure out how to do it with equations. And so I just threw in the towel and did it this way. I did it with brute force. And it even took me a while to get used to having to do it with brute force. Like even this time I was just like, oh, obviously, if this number's bigger, the force is too close to this point because it's sagging it down. But then when this number gets bigger over here, at 0.7, this number, now you're sagging this one down. So we got to even it out. Okay, hell yeah. But now we are actually going to do the problem Well, maybe we should still, do this problem, and I haven't done that yet. I've done this problem completely with the math equations. That's what we're going to do next. But let's stick with this being 234.5. I'm going to store that as x, and let's do that one using the equations that we know. Okay, so we want an x of 234.5. We're still doing the problem where this one is 200 millimeters. That's the natural length of that spring. This one has a natural length of 250 millimeters. Okay, we're going to put a weight and then we're going to move a p. So one thing here to do is do your free body diagram. And this is what I'm really good at teaching now. So basically, you just want to come in here and then dot out the object that you want to do the free body diagram on. And so we just did that. We just cut it out of space. And just think about that. If you cut it out of space, it's still in the universe. You know what I mean? And since even though we're on Earth, we're still in outer space. You know what I mean? You can make that association. Just because you blast off in a shuttle to get away from the Earth's gravity, and then you feel like you're in outer space. You know what I mean? Technically, everything is space. Everything is outer space. So, and this will be a very helpful way to do free body diagrams, because now what we're saying is we have a chunk of material that has a mass. Cool. You know what I mean? It's got an m. We're gonna say, so now we want to figure out, and then the most important thing about a free body diagram, this gets back to Newton, is we observe that it's not moving. So every problem that we're doing in statics, in material mechanics, is like, hey, look at this bridge. Hey, look at this object. There's no motion. That is just like 3 check marks, because that sets it up. Because now, but we can still cut it away. We can still cut that object away and be like, whoa, we have an object with mass, and unless we're in outer space, I would draw the Earth in. You know what I mean? Hell yeah. So you have the Earth in here, but this thing is technically still floating above the Earth because we chopped it out of space. There's no ground that we see underneath here. It's just all air. Okay, so the first thing is like, why is there, hey, this weight, like in the center of mass, there is a weight. Why? And this weight is a force in newtons. It's 25 newtons. And the question is why? Well, it's because you have a huge Earth here, and the gravitational equation for gravity is there's a force multiplied by the gravitational constant, mass of your object, mass 1, times the mass of the Earth, divided by the radius between the center of mass of your object to the center of mass of the Earth, which this distance is just, who cares? It's the radius of the Earth. You know what I mean? So from the center of this is just the radius of the Earth. And if you go through here and do this, you would find out that the this object, I mean, if you figured out what the mass of this object would be, this equation would give you 25 newtons. I mean, go do it. You know what I mean? Figure out, and you'd have to do it in reverse, because you basically F equals ma. If you were trying to find the acceleration due to gravity, you would have like, hey, I want it, like these are the two you should always. Whoop, there's like a butt or something. All right, hell yeah. So let's say you'd want to, let's say this thing is just drop, it's stationary, and you want to drop it, and you want to find its acceleration. You know what I mean? So you put these two equations together, and you say that the acceleration of this object is the force divided by the mass of the object. The only force on here, if it's just floating above the Earth, is the force of gravity. So it's force of gravity divided by the mass, which is just this number divided by m1. So the m1's cancel, and all you're left with is that the acceleration of gravity is gravitational constant, mass of the Earth, radius of the Earth squared. This is squared, I apologize. And guess what this number is? 9.8. And like if you don't believe that or whatever, you should know how to do this one by heart. You know what I mean? Because the gravitational constant is like what, 1 times 10 to the negative 11? No, it's like 6. It's like 6. It's like 7. 7 times 10 to the negative 11. Mass of the Earth is a number times 10 to the 24. I think 6 again. So yeah, and you can really do this really easy. Just think of the devil, because this, you turn this into 6, turn this into 6, and then the radius of the Earth is 6 times 10 to the 6. Holy Toledo! But you're squaring that, so this becomes 36, or 2 6s. It's 6 times 6, and there's 2 6s up here. Those cancel, and then you're just left with 10 to the 12 downstairs, and then 10 to the negative 11 plus 10 to the 24. Well, 10 to the negative 11 goes downstairs, so what you're left with is 10 to the 24 divided by 10 to the 11, 10 to the 10. So now you got 10 to the 24 divided by 10 to the 21. And I feel like I must have messed up someplace. Yeah, I thought the mass of the Earth was 10 to the 24. But you know, 24 minus 21 is 10 to the 3. That's not the acceleration of gravity. Acceleration of gravity is 9.8, or 10 to the 1. So where did I go wrong? Radius of the Earth, is it 6 million? 6 million meters? Did you get 10 to the 12? Then that leaves 10 to the that leaves, oh yeah, no, I think we got it right. I think I just did my math wrong. No, duh. This is what blows my mind. This was 10 to the 12. I changed it to 10 to the 10. No, we did it 100%. So yeah, 10 to the 11 plus 10 to the 12 is 10 to the 23. 24 minus 23 is 10 to the 1. And you get 9.8, you know what I mean? So you should always be familiar with this. Because this is, the fact that this is a force is you shouldn't overlook it. And the only reason something with mass is heavy or has a force, like when you know what I mean, it's because the Earth is underneath your feet, for the love of God. And it doesn't matter whether you're on Everest or at the sea level. It's basically about the same, 9.8. You know what I mean? Okay, so we got that. So that's a force. But let's go back to chopping this into outer space. So if I just have this and chop it, and we just pretend like it's in outer space, I just identified one force on it. So if this object was in outer space, and I could generate a force, or there was a force on this object that was detectable, well, guess what? Newton's equation says F equals ma. You will observe. So if there is a force, you will observe acceleration. That's what this equation basically says. And if you observe acceleration, you observe motion. So you definitely will observe velocity. But not only will you observe velocity, you'll observe a change in velocity. Or definitionally, this thing will not only move, but will be speeding up. You know what I mean? And as long as this force exists, it'll speed up to the end of time until that force goes away. You know what I mean? So that's F equals ma. Change in velocity due to a force. But again, let's go back to statics and material mechanics and making bridges. Like, we do not observe this. We chopped it out, so it's in outer space. We identified the first force. But guess what? We do not see this thing moving. We see it stationary. So there has to be some forces this way. You know what I mean? Booyah. And so that was a very half-hour roundabout way to say, sure, there's a force. There's a force at this point, and I'm going to call it force 2. Even though this is point B, this is already length 2, spring constant 2. I'm going to call this force 2. And over here, I'm going to call this force 1. That's what I've been doing all day. Cool. And then L over 2 is right there. L over 2, length over 2. Okay, so even just like right here, now we know that this force 1 and this force 2, if that's all we have, if we just have the weight on it, and we have this force and this force, well, we get our first equation, because it has to be hovering. You know what I mean? It has to be not moving and accelerating, because we observe that it's not moving and accelerating. So that means that these forces have to balance. So that's why some professors are like, hey, force balance. I don't do that. But we just know that we go to that F equals ma, and we don't. If we do observe a force, it's all right to observe a force, but if we still observe no motion, we have to say there's an equal force in the opposite direction, kind of equal and opposite. That's more Newton right there. So that's where we get, hey, the sum of the forces. It's all right to identify a force. Doesn't mean this thing's just going to be moving, because we might have a force in the other direction. So we're going to say that, hell yeah, this is the y direction, this is the x direction. So forces, sum of forces in the y direction have to sum up to 0. So we have force in the y direction, F1 plus F2. And then this is not in, it's in the negative y direction, minus W. Those have to equal 0. So booyah, we got our first equation. All right. So now let's say we just introduce this force P. And so let's say force 1 and let's say force 1 is equal to force 2. You know what I mean? And we don't have P here. Would that make perfect sense? If this is right in the middle, you know what I mean? Like we said, it's like, hey, these are probably balanced. If we put W all the way over here, well, then force 2 would be 0. So let's do that. Let's put if for whatever reason the weight is only over here, and then this has no weight over here, force 1 would equal the weight, and then force 2 would equal. That's a bad analogy, because weight is due to the mass. So well, let's go back to how it's drawn, and then let's just start putting the force P right here. Well, and we're going to say force 1 and force 2 are equal, and then they're going to equal to this weight, but then we just put in another force. And we put it right here. Oh, this is a bad analogy. So let's draw this in, and we're gonna say this is very, it's like foam. You know what I mean? Very little, no mass. And what we're gonna say is that we're going to and we're gonna put downward force on this. For this one, downward force there and downward force there. No, that's not how I want to do it either. Oh, for the love of God, how do I teach this? Yeah, well, let's do F1 here, F2 here. Well, what I'm getting at is, like, let's say these are equal. F1 is equal to F2, and everything is just kind of nice and balanced. I guess we'll have to go back to this weight. The weight's right here too. Oh, I guess I'm getting at, if you put the P right, if you put the load right here, F1 and F2 cannot be equal. I mean, I think intuitively we already proved that. We said, hey, if we put load P right here, this F1 is big. This F1 is bigger than F2. You know what I mean? But then if we come over here and put the load over here, this F2 is bigger. Like this load P is only taken by F2. And then whatever the weight is shared evenly. You know what I mean? The weight's always shared evenly, but wherever we put that P. All right, let's explain this one more time. All right, hell yeah. And what we're getting at is, cool. I said if I had a weight here, I had to have some sort of equal forces in the other direction to balance out that weight. But now let's say I just have this, and it's massless, and I'm actually just going to put a force over here. You know what I mean? Just a random force. Well, and then I'm gonna actually put a force up this way. You know what I mean? So if I get this, if I have a force down over here and a force up over here, what's going to happen to this? It's just going to start spinning. So that's another one of F equals ma. The motion that you might see is like spinning. You know what I mean? So you have, if you have a force over here and a force up this way, you know what I mean? This thing is just going to be spinning around in a circle. And not only is it going to be spinning in a circle, if this force is constantly on this point and this force is constantly on this point, is going to have some sort of omega, or like radians per second, but it's going to have some sort of alpha, some radians per second. Just like a change in velocity, just like something with velocity has motion, but acceleration is like, whoa, it's like speeding up. So this thing's going to be spinning, and it's also going to be speeding up while it's spinning, just spinning faster and faster as long as these forces are involved. So if I had this setup, and let's draw it one more time over here. If I have a downward force and then an upward force, because like I said, we already chopped this object out of outer space, and if you go back to where we chopped it out of, we observed no motion. So if this was our diagram, force down, force up, we would have to have some other forces to balance this spin. And so this spin, you know, what's happening here is called a torque. I mean, like, whoa, like if this is our halfway point, L over 2, and you're like, hey, you're just you're a pivot point right here. You're like, well, how much torque are we generating? Well, torque is force times distance. So right here we'd have the torque here, and then we do it with the right-hand rule. So this force times this distance, the force is with the sweeping fingers, and it's going to be a negative. So we have negative, the force is F, the distance is L over 2. And then over here we have another force that's up. So sweep the fingers up, still the torque is in the negative direction, so we got minus F, L over 2. So the torque is going to be half of FL over 2, so it's going to be just FL. So this torque is FL. And engineering students should be doing this one on the daily, is like just going back through and just doing that diagram and be like, oh, never thought of that. We chopped this object out of outer space. We realized that when it was attached to the bridge, it had no motion, zero velocity, zero omega, you know, just no spin. It's not moving anywhere. We built a bridge, right? And then maybe we observed a force over here and we observed a force over there. You're like, well, okay, we definitely can observe those forces, but if that's the setup, that would generate a spin. We don't see a spin, so there must be some other forces that are balancing. So right here, we might have a downward force balancing, like a balancing force, and an upward force balancing. Those would generate, so we would, then we would have, you know what I mean? You would have F times this distance, sweeping this distance would be negative, but then B would be, you know, thumb would be up, B is a force upwards, so that's going to be a positive torque. Over here, the fingers are still sweeping where my thumb, our right-hand rule shows that this is an upward torque. And I think more classically, it would be as if you have an object kind of like this, where you have the force down, the force up, and then so these are like where would I draw? If I drew a line here and a line here, this would be a good experiment to do. Is like, where do I put the arrows? Do I put the arrows this way or that way? So put your right hand rule, put your thumb in kind of the center of mass of this object. This is going to be a downward force or downward torque, and this same thing, downward torque. So these two forces, if we push them out to the side to balance it, have to be a positive torque. So there you go. So this arrow's got to be that way, and then this arrow has to be that way. So these would be the balancing forces. Now this is balanced. And if this distance is 2 and this distance is 1, then we can say, and this is where they get to the definition of a couple. You know, I think it's easier just to find the center point and be like, okay, half the distance between these two forces times that force is you know, this is negative a half, and then over here is negative a half. But that's where they just say, hey, quickly, if you have two identical forces with a distance between them, then the couple, the torque generated, is just pick one of the forces, because they're the same, and then multiply it by the distance between the two objects. So that's where people do, but that's how they got that. That's where they're going like real fast and being like, oh, I see a couple. The torque on that couple generated is just FL. So over here, you would be like, okay, identify that these two forces are the same. The distance is 2. The torque due to that is going to be a negative 2F. And then it's got to be balanced by, And then we have a positive plus positive. We got same forces here, distance of 1. So that's going to be a positive 1B. Cool. And then these forces, these torques are going to add up to a net 0 torque. So basically the torque on this object is if we observe that it's not moving, the net torque is going to be 0. So net torque might be the better way to think of it, but that's also called moment, M. M for moment, and then we say the sum of the moments are equal to 0. And if here's the center, we say the sum of the moments at the origin is equal to 0, so we're going to sum from the origin. So if we did that and we still said that we're going to take half the length, we're going to do this. We're going to go, we're going to say negative F times the distance of 1 minus F times the distance of 1. See, we're still in the negative torque. Now we go over to B and we say, hey, that's going to be a positive moment. And we say B times the distance of a half, 0.5. And then over here, plus B times the distance of a half. Cool. And then that's got to equal 0. And then we get this same equation. Minus 2F plus B is equal to 0. But hell yeah. But that's going to be the prerequisite for doing any free body diagram. And even just the fact that you know it, you should still go back and do it from this basic level. Because it's just, one, you might forget. You know what I mean? And I don't think it settles in. I don't think it settles in until, especially when, like, yeah, I've watched engineering videos, and the engineer's like, oh, don't you remember this is a couple? Well, it's like, let's say you forgot. You know what I mean? If you forgot, and then somebody just told you, you have no idea where that comes from. You know what I mean? You have no idea that, oh, I take half the length times this force, but oh, it's going to be the same as half the length times that force. So at the end of the day, it's just pick one of the forces times the total length. Because if you don't actually do that, then memorizing that a couple is just, hey, pick a force and then the distance between the force, as that's the definition of the torque on a couple, it's just going to do you a disservice down the road. Especially when you get into material mechanics, when you're like, everything, especially with shear, is like, whoa, we observe a downward force, like a cutting force on this side of an object and a cutting force on that side of the object. But like we said, we observe that, hey, we're not observing motion until like maybe it breaks. But if that's the case, if we had a force this way and a force that way, and this thing was just floating in outer space, it would just be spinning nonstop and spinning faster and faster and faster to the end of the time. But we do not. We observe a stationary chunk of metal with a force on it this way and a force on it that way in a vise or in a cutting machine. So the only way that piece of material can remain stationary is if you have these balancing forces this way and that way. But that's incredible, because now you do have shear forces this way and that way. When you start to tear something this way and that way, at the same time you're tearing it this way and that way. It's amazing. It's amazing. Okay, hell yeah. So now we go back and use that concept for what we did. So the reason why I did that is because now we can show that if we put this P over here, get some more time on the clock. Alright, heck yeah, we're back. And so what we're showing is that we have a free body diagram that shows that if we put a load here, that we're still observing that this thing has no torque on it. It's not rotating. And so that means that the torque that are generated, let's say from the center, has to be, all the same. So we have F2, this force right here to this, that's in this spring times this half the length is balanced. So this is an upward torque. It's going to be balanced by half this force times half. The weight right here, let's say we're taking the moments from the center. this weight doesn't spin it. As long as we're right here, this weight's not spinning. If our hinge is right here, but if we do put the load right here, it's got a positive, and so this whatever this distance is between here times P, that's going to be a positive torque. So we just said that F2 times half the length was positive, this was negative, and then we have another positive. So this shows that, hey, because the distances between F1 and F2 are the same, this one's positive, but this one's positive, and they have to balance with this one being negative. So if that's the case and the load's over here, this force has to be, F1 has to be bigger than F2. You know what I mean? So just visually, that's kind of what's going on, is like, whoa, if I put the load over here, F1 has to be bigger. And that's just from intuition too. We've already said that if we put the load right under this spring, this ain't taking anything. And if we put the load in the center, well, now both are equal. You know what I mean? The force in both sides are equal. It doesn't even matter what the springs are made of. This one might be real strong because it's longer. Or I don't know. This one, or whatever. We can just say one's stronger and the other one's weaker with the spring. But as long as we're observing that this thing is stationary at the same as long as the weight is in the middle and the load P is in the middle, and then we're observing that the thing is horizontal, that definitely means that this force 1 is equal to force 2. So hell yeah. And let's go back to this drawing, because we can also show so we're gonna kind of take that shape, and we're going to say this is, well, I don't know, we're going to go 1 and then 2. So there you go. Distance 1, distance 2, a downward force, upward force, and then, hey, that's negative, so we got to balance it with our balancing forces. And we took the moments about the center. We already did that. But now let's take the moments about, we're going to say this is point A and this is point B. So right in this little diagram, we're going to take the moments about point A. And we're also going to say that's equal to 0. It's that, hey, every point on here, we're observing the thing's not rotating. You know what I mean? That's not a hinge, and this thing's not rotating around this hinge. We're not observing that. So moments are about A are equal to 0. So let's go through all the forces. Hey, this force, B, is positive torque. Distance is 1. So B times 1, this distance is, F is negative. So we got negative F. What's its distance? Well, it's the perpendicular distance from A. You know what I mean? So that distance is 2. Come over here, this balancing force B, well, it's directly in line with A. So it can't, this force is just tugging on A. It's not causing this mass to rotate. You know what I mean? This force doesn't cause this thing to rotate and rotate. And then this other one right here, this force, because it's directed through point A, also doesn't cause it to rotate. And the analogy of that is like, go try to open a door by gripping the hinges. And a bird's eye view of that, let's say you had the hinges, I mean, still, if you gripped them with your fingers, the center, the exact center is right there. So you can still grip and still maybe pull the door, because there is a small distance there, in between there. But if you molecularly got to the very center of that door hinge and tried to turn those molecules, you just wouldn't be able to. The torque you would be able to generate wouldn't be anything at all. So forces, so right here, you're generating a force this direction, kind of through the center of the hinge. It's very useless. That's why you go over here to the doorknob and do a torque that way, and then heck yeah, there's the distance of the door. That's the width of the door. That's why the doorknob is there. You put a force on it. Cool. So here was our moments at A, and we found our 2. They're going to equal 0. So this says that B is equal to F2. So there you go. Now, is that what we got from summing about the center? Summing about the center, we got F. So summing the moments about the origin. And we're going to do this one at a time. So we have that force times a distance, perpendicular distance of 1. This force B, and that's negative. That's a negative torque. B is a positive torque. The distance is 0.5. So we got B at 0.5. And then we have, and again, this would just be B minus 2F is equal to 0. That's what we're shooting for. Okay, and then we're going to go over here to this F. It's going to be a negative, same thing, negative F distance of 1. We're going to go up to this torque. It's going to be positive B 0.5. So now we're going to get 2 of these F's, so negative 2F, and then we're going to get plus B is equal to 0. Well, what do you know? So now we're proving that you can take the moments about any point, and about any point it has to be 0. And that's just a fundamental. We chopped this object, you know, even though it's part of a bigger structure. We did a free body diagram, chopped it into outer space, and then we're like, hey, we observed a force here, but we can't just have an unbalanced force, and you know, because that might generate torque, especially if we have a couple. So we have to have balancing forces to balance that out. So that is the full rundown. You know, kind of back to our problem. That would be very useful in being like, oh, okay, that's why our next equation, after equation of just summing the forces in the y direction, so this thing doesn't just move, is summing the moments, and we can use that to sum the moments about any point. All right, so let's grab a new sheet of paper. And we're going to do our official free body diagram and just kind of make it nice and clean. We're going to have a force 2 right there, a force 1 right there, a weight in the center, and then we're going to say, hey, now this P is at some distance x. You know what I mean? From that, so just like that. But now we can sum the forces in the y direction are equal to 0. So we're going to get F1 plus F2 minus P minus W is equal to 0. Now, I like sometimes to just say, hey, kind of do like if I see 2 up and then 2 down, I know that I can take these 2 to the other side. So I can go F1 plus F2 is equal to P plus W. And this is just more intuitive. I can look at this picture and say, hey, F1 plus F2 has to equal P plus W. You know what I mean? Because now we're talking, you know, in the y direction. We have nothing in the x direction, so that makes this nicer. But I might just go right to this. F1 plus F2 is equal to P plus W. So now let's sum the moments about point A. So this is point A, and that's going to be equal to 0. So we're going to go through with our right hand and say, well, let's do this F2 first. So we have F2 times the distance of L, and that's going to be a positive moment. Now we're going to do F1 goes through point A, so again, we proved that there is no moment due to that force. There's no torque due to that force, but we do have some negative torques due to P and W. So we got negative W, and then we're going to multiply by L over 2. That's the distance from point A for W. It's half the length. And then we got minus P, and the distance is X. Okay, now this has to be equal to 0, so we just did it. And then the other thing, just how we did this, we could be like, whoa, F1 plus F2 is equal to P plus W. We can do the same thing for the torques. We can, hey, come in here at A and be like, okay, we have a positive, and then we got 2 negatives. So I can just say, and we'll put more time on the clock. All right, hell yeah. So I can just come in here and look at this, and I got F2 is positive, P and W are negative torque. So I can just say F2L is equal to WL over 2 plus PX. You know what I mean? So that's the same as that. It's just faster, and sometimes it's a little cleaner. You know what I mean? Because then you don't have to worry. The less times I see negatives, maybe I'm going to make less mistakes. So there you go. So there's our 2 equations. And now anytime you're trying to do this from like a mathematical proof perspective, I've been you know, really focused on like, hey, we have one equation that says F1 is equal to Yeah, this equation says that F1 plus F2 is equal to P plus W. That is, we're going to totally take this from the fundamentals. Is like holy Toledo, because even just like right here, you're like, cool, we did that one, but we know from perspective that, hey, this is just one equation, and we don't know what F1 is, and we don't know what F2 is. But still, this is cool, because let's rearrange this equation and say F1 is equal to P plus W minus F2. Well, from our, you know how we have our calculators and we have a y equals, some x plus, mx plus b would be a line. Well, right here, we have, you could say that this is your y value, this is your x value, and then even further, this is saying, hey, we have a function, f1, as a function of f2. You know what I mean? I bet you've never thought of that. This is the same thing as saying, hey, I have a function with respect to x. That's the same thing as saying y, I have a function y with respect to x. You know what I mean? Well, let's say it's ax squared plus b x plus c. You know what I mean? So in general, like anytime you get one, and this is just me trying to get like better at math and better at when I'm doing engineering, not being like, okay, I have one equation and two unknowns, so I just need another equation, and then once I get this, two equations with two unknowns, I can just solve it. It's like, no, you know what I mean? Because what we're trying to do is like trying to get more of a familiar with like, hey, like let's get equations that solve many different scenarios. So even just right here, we have a function of f1 with respect to f2, and there's our f2. So in our calculator, we turn this into x, and this is our y, our y value in our TI-83. So we go, for our problem, P is equal to 18 newtons, W is equal to 25 newtons. So if you got a TI-83, that's why I'm doing these videos for the TI-83 calculator. And we're going to go 18 stored as alpha P. So now we can bring up alpha P and it's 18. 25, this stored button, alpha W, and we got alpha W bringing up as 25. So now in my calculator, and then you may not even known that you can just throw in letters. As long as the letters aren't Y and X, maybe you could even do Y, I don't think so, but you have to, you can throw in, I'll have to experiment, but definitely X has to be your variable in this. So we got alpha P plus alpha W minus X. So there you go, and we can zoom and then fit that equation. So there you go. There's our, and we can trace it, and obviously we could go window. We're not doing any negative y's. So there you go. So there we go. We have an equation for let's go value 5, and and then you can get used to what this is saying, because it's saying hey, if this force 2 is 0, you know what I mean, this force right here is going to be, F1 is going to be 42. But didn't we say W? We already have W as 25. W is 25, so, and we're saying that's equally distributed. So 12.5 newtons here, 12.5 newtons here. So even just we're trying to learn something about this equation, and when we turn it into this equation and put it into our calculator, the force in either of these has to be a minimum of 12.5. So we just come in here and do 12.5, graph that. So that is our high end. So now we're going to even go y at 15. Oh, whoa. X at 50 graph. Okay, so there you go. So now we have kind of what's going on here. We're going to trace it, value 40. Value at 12.5. No. What is this saying? It's saying when we throw in a value of 12.5, trace, where are we at here? Okay, so when F2 is 30 newtons, so when there's 30 newtons over here, then there's going to be 12.5 newtons on this side. Cool. And I guess what I'm also thinking is like, hey, rearrange it again for F2. So you can go F2 is equal to P plus W F1. And this should be F2 right there. And then let's throw this into our calculator as X. So then we're going to have alpha P plus W minus F1. So just rearranging this. P plus W minus F1. I guess we'll write that again. F2 as a function of F1 is P plus W minus F1. And then we're going to graph that. It's the same line. You know what I mean? So, so that's very interesting. So when 12.5. Alright, so what the hell is this saying? It's saying when the value of F1 is 30, which is 12.5 plus 18 is 18, 19, 20. That's 30, yeah. So when P, more light. Alright, holy Toledo. Yeah, we're just learning on the fly here, and that's going to be alright. Take just okay. So yeah, so I mean, if we put P over A, you know what I mean, or over B, that's max. So we got 30.5. So when we go to a value of 30.5, the other value is 12.5. Cool. But then if we oh, that's why my window Y max 50. Okay, this will make more sense. I just didn't know what side of the graph I was on. So yeah, if you go down here to the force being if F1, it doesn't matter what's the same, but if we're saying F1 is 30.5, then F2 is 12.5. But then if we're saying F1 is 12.5, so we're going to come in here right here at 12.5. I don't know how to make a vertical line. How do you make a vertical line on a calculator? I'm sure there's a way to do that. I don't think so. But if we go to 12.5 right there, then yes. So if I had a vertical line, then here's the relationship. So if F1 is 20, let's go to 20. F2 is 23. The force where they're the same would be 21.18. All right, more time on the clock. All right, holy Toledo. Yeah, and obviously, if the P was right in the middle at 18 and the weight is 25, we'd have 18 plus 25 divide by 2, and you'd get 21.5. So if we go to our graph and go to a value of 21.5, obviously both F1 and F2 are both 21.5. You know what I mean? And again, I have to say that we're still doing the easy problem where H is not involved. You know what I mean? We'll get to that. We'll get to that. Okay, but now we can start. I feel like we have enough intro, and we can just start crushing it out. Hopefully. Free body diagram. F2. F1. the weight. We're going to have x, or a p at some value of x. We're going to have forces in the y. F1 plus F2 is equal to P plus W. Moments about A, we're going to have F2. And it doesn't, even if you were saying PX, even though it's a negative torque, but you're just, you know, it is, you don't have to worry about the equal signs. But obviously F2L is positive, so F2L is equal to PX WL over 2. So there's our torque equation. So we have our y equation, our torque equation at moments. So this is moments at A is equal to 0. This is sum of the forces at y equals 0. But hell yeah, equation 1, equation 2. Okay, now we need to go back and be like, whoa, we got springs, and we need to know what springs do. So again, force of a spring is K. You know, you might see this Kx. That's not very useful to me. I always change it into the force of a spring is K times change in length. I always use delta L. It just visually looks better. We already have an X here that has nothing to do with the springs. So I'm just going to kind of erase this. And this is our force on the spring. Okay. Now this was the one hiccup I got caught up into with this problem, because I just went to, hey, if these springs are both at their natural length, and then we have weights and loads on them, and we're saying it's still horizontal, that change in length of spring 1 is going to equal the change in length of spring 2. Change in length 1 is equal to change in length in spring 2. Now, that is an accurate statement. That could be our third equation. But I think it was important for me to take this equation just a little bit farther, because you have to remember that a spring has a natural length, you know, so we're going to call it L naught. That's how I'm going to do it. So let's say it's spring 2. Spring 2 has a natural length L naught, and then spring 2, if you put a force on it, can change its length. So here's the change in length in L2. Cool. And now we're saying that the force is equal to the spring constant of spring 2 times the change in length of spring 2. Cool. But it is important to know that, hey, the length, hey, we have a third equation here that says maybe like the length total. And I'm just going to say it's just the length of 2. The length of the spring 2 is equal to the length of, I'm just going to do another equation. Length of 2, which is kind of the total length of this, is equal to the length of the initial length of the spring, the resting length, plus the change in length of 2. So even if this spring goes the other direction and gets crunched in, here's my change in length. We could do that. So length 2 is equal to length 2 initial. Length 2 initial is 200 millimeters. Plus, hey, we have a negative change in length. So minus, let's say 30. You know what I mean? So then we would have 170. Length 2 in this case would be 170 millimeters, which will come into the problem that we'll do next. But we're still doing the problem where, hey, both these lengths, this is going to be 200 millimeters, this is 250. Both are positioned at their natural length, because it just helps visualize that easy problem all the way through. Okay, so we have this equation that says, hey, now we have an equation for the length of 2. And if we do that same thing as being like, hey, as f is a function of x, you know what I mean? We can say, hey, we have a function of length, we have an equation length 2, and hey, this is just given. This is a constant, but our change in length we don't know. So we have length 2 as a function of the change in length 2, and that's going to be equal length 2, the initial length plus the change in length of 2. Cool. All right, and we can do the same thing for length 1. Length 1 is equal to length 1 initial plus the change in length of 1. So just very simple equations. So these are equations, they just pop out of all springs. So it gives us more. So now we have 1, 2, 3, 4, 5 equations. And we can do the engineering thing of like, let's count unknowns. Hey, we don't know F1, we don't know force 2. We know these loads, we're given those. We know the length, we're given that. We don't know X. So right here we have two unknowns, one equation. Hey, we get an extra equation, but we have 1, 2, 3 unknowns. Shoot, 2 equations, 3 unknowns. Hey, we get an extra equation, but we don't know either of these. So now we have 1, 2, 3 equations and 1, 2, 3, 4, 5 unknowns. Okay, now let's go down to these equations. And we get one more equation. We know this. We still don't know these, but now we don't have to count them twice. You know what I mean? So now we already counted this one. So 1, 2, 3, 4, and X is 5. And then now we have 6. So we have 6 unknowns and 1, 2, 3, 4 equations. So now we come down to here and say, hey, we have 5 equations. And did I get 6 unknowns? Do I have 6? 1, 2, 3. I think we know those. 4, 5, 6. And now we have one more at 7. So we've got 7 unknowns. Length 1. Oh. Let's. I don't know where I'm getting confused, but let's take these 3 equations because hey, we don't know length 2, and we don't know the change in length. But here we do know that here's an equation. So yeah, we have 1, 2, 3, 4 unknowns, but here's an equation that relates both those. So that's going to give us. Holy Toledo. I don't know why I'm wigging out on this one. I'm just learning how to teach, and this is probably not the way. This is definitely not the way to just show the learning process. But that's what math is, just like, whoa, I think I'm like at a, running into roadblocks that I'm just creating on my own. So here's the force equation, the moment equation. 1, 2, 3, 4, 5, 6, 7, and we got 5 equations. Holy hell. Alright, well, let's talk more about just forces of springs, because I think that'll help. So we have the force of springs equation. Like we wrote them down. We started to write them down. So yes, the force of a spring is so the force this force in 1 is only due to the spring. So whatever happened at this point 1 or point A. So the force in spring 1, which is right here, F1 is equal to spring constant 1 times change in length 1. Cool. That means force 2 is equal to spring constant 2, change in length 2. So hell yeah. So we have 2 more equations. So we have 6, 7. And we already counted 7 unknowns and we got 7 equations. I just didn't realize this problem required 7 equations. You know what I mean? Alright, so hell yeah. So I feel more fresh and let's get some more time on the clock. Alright, hell yeah. So let's from the start get those equations again. You know what I mean? So free body diagram. We're going to have weight, P, at some X. And then we're going to have F2, F1. We're going to have F1 plus F2 is equal to P plus W. We're going to have the moments, or F2L, is going to be equal to WL over 2 plus PX. And then we're going to have the forces of springs. That says, hey, the force of one spring is the spring constant times the change in length of spring 1. Force 2 is spring constant 2, change in length of spring 2. We're going to say the change in length of 1 is going to equal the change in length of 2. and then we're going to say, hey, we definitely need to go back to that diagram of, hey, length 1 initial, and then we're going to lengthen it, and then we're going to have change in length of 1. So now we have an equation for the total length. So length 1, we're going to call that length 1. Length 1 is equal to the initial length plus the change in length 1. And if you rearrange, and then so we have length 2 is equal to length 2 initial plus the change in length 2. And actually, this seems intuitive, but what we have is a force that says, hey, what the hell is the change in length? And so let's do that. Force 1 is equal to K1. What's the change in length? Well, it's the length, it's the final minus the initial. So change in length, anytime you have change, is final minus initial. So length final is just L1 minus length 1 initial is L1 naught. That's what I'm saying that is. So hell yeah. Force 2 is spring constant times length final L2 minus L1 naught. L2 length 2 initial. So booyah. So even just right here, what we did right there was, hey, we took our equations. So we took these two equations, we solved them for the change in length. And if you can't see that, well, let's take this one down here. Let's solve for change in length. Change in length 1, we bring this to the other side. It's length 1 minus length 1 naught. Well, that's exactly what we put in right there. See how we change in length 1, change in length 1, and we put in that into there. Same thing there. So once you get the 1, 2, 3, 4, 5, 6, 7 equations, cool, you have 7 unknowns. And it's easiest to start kind of at the simplest, put the simplest into the simple, you know what I mean? So hey, this is just, one thing minus one thing. Hey, that's going to be really simple to throw in those equations. So now I have these equations for F1 and F2, and now I can put those in, oh, and this one could get just even simpler, where I said that, hey, change in length 1 is equal to change in length 2. So, we might want to do that one first. So let's say length 2 is equal to length 2 initial plus change in length 1. And we're going to say F2 is K2, L2, oh yeah, and then we'd solve for, no, that's wigging me out. It's wigging me out. But yeah, we'll definitely have to use this equation. I just don't know when. Damn it. Well, I mean, we can register that this is change in length 1 and this is change in length 2. And so we can say that both these are going to be equal. So we can get, oh yeah, so yeah, we would probably go F1 is equal to K1 change in length 1, F2 is equal to K2 change in length 2, and then we're going to say, hey, these two are equal. So one way to do it is just solve for change in length 1 is equal to F1 over K1. Solve for change in length 2 is equal to F2 over K2. Cool. Now we can just set these equal using this equation. You know what I mean? So then we can just say F1 K1 is equal to F2 K2. Alright. So now we've used these into this equation. And then we used, which maybe we didn't really have to, but then because we used these into this equation and got the relationship between F1 and F2. Alright, we're going to need more paper. And so now we're going to take this and we can say, hey, F1 is equal to K1, K2, F2. You know what I mean? Maybe that's useful because then we can plug that one into this equation. You know what I mean? So now we're going to do K1, K2 times F2 plus F2 is equal to P plus W. Cool. And then you know, kind of all in all, we need to get this equation for X. And so we need to plug this F2 into there. I mean, we need to get an equation with just X and our unknown, and just our givens. So we have P is a given, W is a given, L is a given, K1, K2 is given, P, W is given. This F2 is not given. So we're going to solve for F2 and then shove it into that equation. All right, let's do that. So we're going to factor out an F2. So we're going to go F2 is K1, K2 plus 1 is equal to P plus W. So now we can say that F2 is equal to P plus W divided by K1, K2 plus 1. Cool. Now we're going to, even though this is horrible looking, we're going to shove it into this equation. I'm just going to write this equation. F2L is equal to WL over 2 plus PX. Alright, so now we're going to shove this into there. And so all we have to do is just go this times L, and essentially it'll be that. So we're going to go P plus W times L divided by K1, K2 plus 1 is equal to WL over 2 plus PX. So right now is the first time that we've actually got an equation that has our X value, and hopefully it pops out that 234 or whatever millimeters. Everything else is given. This is 25 newtons. This is 350 millimeters. K1 is 0.3, K2 is 0.4. Again, it's newtons per millimeter. And then L is, you know, so everything's given. So even if you don't want to rearrange this equation, you can use your calculator to solve it. And so I'm going to show you, you have to get one side equal to 0. So you either throw this into your calculator and then go minus, and then equals 0. I think you could do that math because if these were pluses, you just bring everything to the other side. So let's do that. So everything is, and then, so where I put K1 in my calculator is K. So 0.3 is equal to K. 0.4, the letter is equal to J, so alpha J. And then alpha W, alpha P, I just want to make sure all my letters, and then alpha L is 350 millimeters. Cool, so now I can just plug this into my calculator. I can go parentheses alpha P plus W times L divided by parentheses alpha K divided by alpha J. K2 is J, my calculator. And then I'm going to go plus 1, parentheses. And I got my parentheses game down. I'm trying to use less parentheses, so even this is going to do the J over K first, and then calculators do the PEMDAS. So it's going to do this plus 1 second. So I'm all good there, and I don't have to use any extra. And this is going to go multiply, and then divide the whole thing. So you can have as many multiplications, but then the second you get to divide by everything, then you got to do at least one parentheses. Okay, moving on, we're going to go minus. So here, I'm just going to do WL, but I don't have to put this in the parentheses in my TI-83, because then I can just go divide by 2, and there is only one term right here, so I really don't need a parentheses for that. But now I'm going to go minus alpha P. X is my X term. So there you go. And then we're going to zoom 0, kind of fits that graph, and we'll get more time on the clock. Alright, hell yeah. So now we're just going to get, we're going to go zoom out, and hopefully it crosses the x-axis. Okay, heck yeah, zoom out. Alright, heck yeah. Camera overheats, so I got to play a little Tetris and then get back to it, doing some laundry too. So anyway, alright, so we got this typed in. And, okay, we graphed it. Perfect. And then we're going to go value. Now, I'm going to go to window because my X value, you know what I mean, should be, it should cross the 0 at some point. You know, whatever the value of X that makes this 0. So we're going to go negative. We're just going to go to 0. Oh, so I probably did something wrong then. Let's see. So this is units, unitless, newtons times millimeters. This is newtons times millimeters. Yeah, this is my moment equation, so it's Newton millimeters. So this is newtons, and this would be millimeters. So everything checks. Alpha L is in millimeters, alpha P, alpha W. Zoom out. Zoom out. Wait, well, window. Oh, there you go. So X max needs to go to 300. So that's where I was getting wrong. And then now I can go window Y min 0. Sometimes the calculators don't let you get out of range. So sometimes it's easy just to be like, whoa, okay. So what's my value of X that I was thinking? Well, 3. No. No, here's my equation for Y. Here's my Y equation. And I want to know what X is. Well, this is going to drop into the 0, so yeah. That's maybe not a good way to do it. But we graphed it, and we knew that my X, okay, again, let's draw this. This is W. This was P. This was force 1, force 2. And then our P is some out here of X. Well, this thing is 350 millimeters long, so X can either be 0 to 350. So that's my range for X that I should be using. X, we're going to go from 0 to 350, and then graph that. Perfect. So now I can, and then I can make a negative. I can make negative 50, and then Y min negative 100. Graph that. Perfect. So now you can kind of visually see it a little bit better. But now I'm just going to go right for my 0 value. Here's my left bound, right bound. So that's the only bummer of typing just an equation into your calculator. It's like, well, this was a moment equation. So the units on here are Newton millimeters. And so there you go. So my 0, X, is 234.7 millimeters. Cool. So now let's take this equation and we'll do it one more step and solve for X. So we're going to get this minus px to over this side, so we're just going to say is equal to px. And then all we have to do is divide by p. So we're going to come over here and divide by p. And then we got to divide by p there. So X is equal to P plus W, and we can do all this. We'll PL plus WL divided by P, and then all this is 1 over K1, K2 plus 1, and that's going to be minus WL over 2P. So we're kind of just hashing this out for X, and I'm not even doing a very good job of doing that. But yeah, these P's cancel, so now we have L plus WL over P. Maybe grab another sheet of paper. So we have X is L plus WL over P, and we got this 1 over K1, K2 plus 1 minus WL over 2P. Oh, and these are multiplied. Yeah, this is multiplied through there. So we can maybe simplify this K1 divided by K2 plus 1. How could we simplify that? Well, you make the denominators the same. So if we make this denominator K2, K2, and then we can add the top. K1 plus K2 divided by K2. Cool. And now, since we're trying to find the inverse of it, the inverse of this is just flip it over. So there you go. K1 plus K2. So that's kind of an easy way to do that. And then so you could go K2 over K1 plus K2 times L plus WL over P minus WL over 2P. That's equal to X. And if we just type this in real fast, we got 0.4 divided by 0.3 plus 0.4, 350 plus 25, 350 divided by 18 newtons parentheses, minus 25,350 divided by 2 times 18. So let's do that in our calculator. So this is going to be 0.7 in the bottom. So 0.4 divided by 0.7 times 350 plus 25 times 350 divided by 18 minus 25 times 350 divided by 2 times 18. See how I do 25 times 350, but then if I'm going to divide by two things, I have to put that in parentheses. You know what I mean? And I don't even have to put this in parentheses. Just at least divide and then that parentheses. I'm just kind of learning different tricks of the trade. Might be other videos down the way. And then we get that x is equal to 234.7. So okay, so we did this one all the way through, but the problem says that these springs are not in their natural length. It says, I mean, if these springs were in their natural length, this one's longer by 30 millimeters. And so this naturally wants to be at an angle. So now, if this naturally wants to be at an angle, where do we put P? Well, we got to put P more this way. So so if this is if we got an answer of 234 divided by 350, so we were putting P this side of the halfway point at 0.67, 67%, 1 minus that, and 33% this way. So 67% that way, 33%. That's where we're putting P if these were just naturally, if the springs were in their natural length. But they're saying, hey, let's shove this spring down here. So just in the natural length, this thing's going to be like that. So we really have to move the load this way to make it balanced out. So let's actually print off some more of those. Well, I'm kind of done. I don't even want to print it. We have this problem so well ingrained that we can kind of just draw it. So we got the first one. And then if the second one was at its full length, it would make it be like that. So we have K1, K2. This distance is 250 millimeters. This distance is 200 millimeters. And they're saying, hey, we're putting it at an H of 80 millimeters. So so we have 280. That means that these are a change in distance of 30 millimeters. See how 250 plus 30, down here, this change is going to be equal to that 280. You know what I mean? So if this is just the natural place where these springs rest, and we're saying that even if we have a weight in the middle, that's just going to be equal on both sides, where it's just going to come down to the same location, let's say. The only way we can actually get this side to balance out is to put the load, so even just right there, we have an idea of like, hey, where to put the load on this side. Okay, so and we could just do that same thing of on this one I don't think I could just kind of crunch out the numbers, because we need to know what's going on here with this spring. So let's get our free body diagram. Our free body diagram is basically the same. We have force 2, force 1, weight in the middle, some x where we have our load P, and we have the same equations. F1 plus F2 is equal to P plus W. Then we have our moment at A, which is going to be F2L is equal to WL over 2 plus PX. And then we have a relationship, spring force is equal to KX. But alright, shoot. So my camera runs out of juice at 10 minutes. And so we kind of got ahead of ourselves. But I think we left off at the force of a spring is KX. And then I don't like X, so I say the force of a spring is the spring constant times the change in length. But then I say, what the hell is the change in length? Well, we say the change in length is the initial length of the spring, maybe at rest, plus, change in anything. Change in length is length final minus length initial. That's one I just got to get better at. It's like, I like using this term change in length, especially for material mechanics, because things do change in length. But that's always going to be the length final minus the length initial. So So yeah, for the spring, we're going to say change in length is, and I did a bad job of that, but we're just going to say, like if we have spring 1, we're going to say the change in length is L1, what we measure, you know, just kind of like what we measure, and then minus the initial L1. L1 naught is what I'm going to say is initial. So force of spring 2. It's going to be spring constant 2 times change in length 2. All right, get more juice going. All right, hell yeah. Okay, force of spring 2 will be spring constant times the change in length of 2, which will be K2, spring constant 2, times the length of 2 minus the length initial. Length final, length initial. Cool. So now what I did was, because we're setting this value at H, our spring over here is, our spring, like let's say our resting spring length comes to here. It's 200 millimeters. Where up here, this one is mounted higher, where this resting spring length comes to here at 250. So this one is lower, and then we have H right here that we're setting this height at 80. So if we start here, we got 80 plus 200. That's 280 to right here. If we start here, we just go 250. So there's going to be a change of 300 millimeters. We're saying if this thing is horizontal, because right now we're trying to figure out, hey, if it is horizontal, we need a relationship between the change in length of this one and the change in length of that one. So here's the first thing to do is just pretend that this bar has no weight on it, and this picture is you know, for its natural length, this spring would have to come down to here. You know what I mean? This is 200. This is 250. But we're saying if the bar is at its, so the natural position of this bar obviously would be angle, but we're saying, hey, we're going to put some load on it that makes it horizontal. So I think the simplest thing visually to do is say, hey, this thing has no weight, it's just made out of foam. It initially is like that. I'm going to put some load over here that makes this side just go down. Let's say I just put the load just on this side. Just enough till it goes horizontal. And that's exactly, if this had no weight, that's exactly what we could do. We just tug on this spring until this goes flat. This point did not move at all, so this has change in length of 0. No change in length over here, but this spring changed in length by 30 millimeters. So now we can use this to find a relationship between these two. So we can say, hey, we can call this the change in length of spring 1. So we can make an equation that says, hey, if we start here, we're going to go H plus 200. That's going to be equal to 250 plus change in length 1. You can throw in the numbers or just say, hey, H plus L2 naught, which is the initial length of spring 2, is equal to L1 naught plus change in length 1. And let's see if we got anything close to that. So I'm going to write that right here. H plus L2 naught is equal to L1 naught plus change in length of 1. Okay, so what I did was say H plus L2 naught is equal to L1 naught plus 30. So I just called this 30, but obviously we could call it the change in length of 1, which I probably did at some point. Let's see what I got here. H plus L2 naught plus the, so I said, hey, realistically this thing is going to have weight and it's going to be sagging. So this one is going to come down here, and this one's going to come here and farther. And so we're going to say H plus L2 naught plus the change in length of 2, spring 2, is equal to L1 naught plus change in length of 1. Cool. So both these two equations apply. And what I started doing was like, rearranging this one for the change in length at 1. So I just minus this one over here, and then I minused this one and put it right there. And then, so that's what I got. And so now we're back at it. So I thought I could simplify this one by saying, hey, the change in length of 2 is L2 minus L2 initial. It's final minus initial. And so that's kind of where we're at. plus L2 minus L2 initial. So now I can cancel out these two, and I can get change in length of 1 is equal to H minus L1 naught plus L2. I don't know if that's useful at all. Alright, but the whole idea here was, hey, we have one equation, two unknowns. And then we did the moment equation. Two equations, we get three unknowns. And then we use the force equation. So we got 3, 4. So we have 4 equations, but we got 2 more unknowns. So now we're up to 5 unknowns. And then we use this equation that relates the initial lengths. But this is all just given information, so this really doesn't help us much. But here's a fifth equation, and this says that oh no, because these three equations, this gives us. So we got 1, 2, 3. Oh no, we're right. 1, 2, 3 unknowns, 4, 5 unknowns. This equation is a fifth equation, and none of the things are, see, change in length 1, change in length 2. So all this fluff was probably unnecessary. So we got our 5 equations. So let's do that one more time. We have F1, F2, W, P, X. We have K1 on this spring. Oh, so sorry. This is 1. This is 2. K1 is 0.3. K2 is 0.4. L1 naught is 250. L2 naught is 200. H is 80 millimeters. And equation 1, F1 plus F2 is equal to P plus W. Moment equation, F2L is equal to WL over 2 plus PX. Equation 3 is F1 is equal to K1, change in length 1. Equation 4, F2 is equal to K2, change in length 2. Remember that change in length is the whole, or is the length final minus length initial. Due to our diagram, we're saying that here, let's go back, and we're going to say, hey, we have H length 2 naught plus change in length 2. This thing's horizontal, that's going to equal length 1 naught plus change in length 1 naught. So I think we can kind of do that now. Just, it's good to do this as many times as possible, just so you can be like, yeah, I can spit it out. So we have H plus L2 naught plus change in L2 is equal to L1 naught plus change in L1. There you go. And let's see how many equations, how many unknowns. Alright, hell yeah. So we have 1, 2, 3 unknowns, 4, 5 unknowns, and these are the same, and these are given. These are initial lengths given, H is given. Okay, cool. So we have 5 equations, 5 unknowns. You know what I mean? There's no. This would probably be the simplest way to do this. Is just do your free body diagram, forces in the Y, moments about A, and then find that relationship between what's the force in spring 1, what's the force in spring 2. It's related to the change in length. Well, what the hell is the change in length? Based on observation that this thing is horizontal, we see that we have to go, and that's where we start at those datums. You know what I mean? You start at this datum and say H plus L2 naught plus the change in length 2. That is going to be equal to L1 naught plus the change in length 1. And that equation links them. So this equation is your fifth equation that links, you know, the linear relationship between these four equations. So hell yeah. So now the idea is like, well, how do you go about putting these into each other? And because at the end we want, this is the last equation. This is the only equation that has x in it. So this is the last equation. This has x and f2. So I mean, if it's kind of hard to work backwards, but essentially you would want to get an equation that had f2. I mean, once we get an equation for x, it'll just have p, l, w, k1, k2. All the things that are totally given, and h. You know what I mean? It won't have anything else that we don't know. So that's our objective. And it's easiest to do the simplest things first. So you could... So you would want to take this equilibrium equation first and maybe solve it for L1. Oh, yeah. Because this has F2, because we took the moment, this is going to be, you know, if we took the moments about this point, we would have an equation with F1 in it. And then we would have, but we have an equation with F2. So essentially we need to, you know, hey, I'm gonna take this equation. This has got F2, and I'm going to throw it into this one. But it's also got F1. So now I'm going to take this F1 and throw it into here. But then it's got change in length 1. So then I'm going to take change in length 1 here and then throw it into here. But then I'll have change in length 2. So then I'm going to take change in length 2 and then throw it into there, and then I'm going to have F2. So then I'm going to be left with an equation with F1 as a function of F2, and I'm going to throw that into F1. So then F1 will just have F2 in it, which will have F2 plus F2. And then I can solve for F2 and then throw that into F1. And that skill will just get better with, you know, it's like there's probably worse ways to go about solving 5 equations, 5 unknowns. But, you know, that's the way we're going to do it. So we're going to solve this for change in length 1. Change in length 1 is equal to h plus L2 naught plus change in length 2 minus the initial length of 1. Cool. Now we're going to shove this into there. And so we're going to get F1 is equal to K1H plus L2 naught plus change in length 2 minus L1 naught. Cool. And now we got an equation for F1. Oh, but it's still got this change in length 2 in it. So we're going to solve this for change in length 2. Change in length 2 is F2 over K2. Cool. So let's do that. So F1 is equal to K1 H plus L2 naught plus F2 over K2 minus L1 naught. Cool. So now I did that. Now I have a function F1 and it's got just constants. I just know everything. No, it's got F2 in it though. But that's exactly where we're headed. Now we take this F1, kind of the next step, and second to final, is throw it into this equation. Once we do that, F1 goes away, and then we just have F2. It gets nasty, but here we go. So I'm just going to take this and then plug it into F1. Well, guess what? If this is just F1, I can just do this and say, hey, this is F1 plus, and then it's just easy to, I don't have to rewrite it, is equal to P plus W. So there you go. So now I need to factor this through, and so the parentheses goes away. And then I need to get all other terms that don't have F2 over to that side. And then, so let's do that. So let's go K1H plus K1L2 naught plus K1F2 K2 minus K1L1 naught plus F2 equals P plus W. Cool. So now, and essentially we're doing this just to get F2 right here alone. So now I'm going to go this is plus K1 L naught 1. I'm going to get rid of it. Minus K1H minus K1 L2 naught. So cool, I got rid of those. And now I'm going to factor out an F2. F2 K1 K2 plus 1. Cool. And then I'm going to divide all this by K1 K2 plus 1. Cool. And then this now is called F2. And I'm going to shove it into that equation. So let's grab a fresh sheet of paper, and we'll say F2L is equal to WL over 2 plus PX. And then we have F2 is equal to, well, let's just start writing it in. F2 is P plus W plus K1 L1 naught plus K1H minus, I'm sorry, this is mine, that'll give you a huge hiccup. K1 L2 naught divided by K1 K2 plus 1. Alright, now we got to multiply by L. But we're done. And that's going to equal WL over 2 plus PX. Okay, again, now we have only one unknown. So you have this monster equation that you could just throw into your calculator if you just did this. Minus, minus, you know what I mean, is equal to 0. Now you can just throw this into our calculator, and let's do that. So we're going to go P plus W plus K1 L1 naught minus K1 H minus K1 L2 naught all times L divided by K1 K2 plus 1 minus WL over 2 minus PX. Now, and maybe you shouldn't do this, because all you would have to do is take PX to the other side and then divide by P. Because if you do that and go L divided by P, you know what I mean, on this whole thing, and then put a P here, now you just have an equation for X. So now this is your golden equation for X. And the only other, I mean, and you can say, hey, it is, let's say this is your Y equation, and you want to adjust the H. So now you have a full fleshed out equation that says, hey, I can adjust this H to anything I want maybe, and maybe that's what I want to do. So that's what I did. I said, hey, I just made this my variable. Now with a calculator, you can only make one of these things your variable. Now, and if you just wanted to solve for X, you just throw everything in. So you throw 18 plus 25 plus 0.3 times 250, minus 0.3 times 80 minus 0.3 times 200, all multiplied by 350 divided by 18, all this divided by 0.3 divided by 0.4 plus 1, minus 25 350 divided by 18 times 2, and there you go. That is X. So before we type it into our calculator, let's just see if we got it right. And we might want to be done anyway. And we got to put more time on the clock. Alright, heck yeah. And it's good practice to type monsters into your equation. So we got, I'm going to do 18 plus 25 plus 0.3 times 250 minus 0.3 times 80 minus 0.3 times 200, enter, times 350 divided by 18, divided by 0.3 divided by 0.4 plus 1, and then minus 25 times 350 divided by 18 times 2. And then, hell yeah, we get the right answer. So we get X is equal to 134.7 millimeters. In the back of the book it says X is 135 millimeters. Swear to God you don't believe me, but we are doing problem 2.210. 2.210 is 135 millimeters. So hell yeah. And so yeah, so we're gonna end this video by like, hey, we got it. We got an equation for H because just the way this is set up is like h is the thing that you could vary. You know what I mean? That's what I see. Obviously, you could change the springs out, and then, yeah, you just change your spring constants. But the initial physical setup, that's what makes this problem. Because you're saying, hey, you're gonna mount this spring to where it's naturally resting at an angle, but then you're gonna load it up to where it's back to normal. You know, at the end of the day, that is exactly what this problem is. So let's type this into our calculator. H is going to be our only x value, and it's a function of y. So we're going to go parentheses alpha p plus alpha w plus alpha k. Oh, and then quickly though, because L1 naught is equal to 250, and I stored that into my calculator as alpha m. You got to put a letter on it for something. L2 naught is 200, and I did r. So I use letters kind of to the side sometimes that go vertically. So this is alpha m is the first one, alpha r is the second one, and I just kind of get used to that. Other ones I'll use n and o. You know what I mean? N and O, S and T, or if I need other two values. But I think those are the only values that we have. Alpha L is 350, and everything else is good to go. All right, let's redo this. So alpha P plus alpha W plus alpha K, alpha M for L1 naught, minus alpha K, and then here's my X, it's my only variable, minus alpha K, L2 naught, the second spring over there, the initial length of the second spring is alpha R. Whoop. Okay, and then parentheses, I'm going to go alpha L divided by P, get that out of the way, and then now I'm going to do divide by this. So we're going to go alpha K divided by alpha J. J is K2 in my calculator plus 1. Don't have to do anything else because it does the calculator will do PEMDAS, so it's going to do the division first. It's not going to do J plus 1. It's going to do the division first. So my brother, I was talking to my brother, and he's just like, he's just like, no, I love calculators because they do PEMDAS. And I was just like, oh, I can get used to that now. I can just trust the calculator. See, I just would never do something like this. I would have to come in here and do parentheses, you know what I mean? But I just know now that I don't have to do that. Might as well keep it as simple as possible, and then we're learning skills. Okay, now this whole thing was a multiplication and a division, and I don't even think I needed a parentheses at the beginning. No, we did. We did a parentheses there and a parentheses there. We didn't put any extra parentheses at the beginning. And again, PEMDAS. We had multiplication, and then division. And that's the last thing it's going to do. Now when we do an addition, it's a completely separate variable. Your calculator does PEMDAS, so it does everything here. And then once you have an addition and subtraction, it's like, hey, new thing. So we go alpha W, alpha L. Now we can do divide by. And here I do need a parentheses. I got to go alpha P times 2. Now if I did, or just, I don't even need to do the times 2 because it's up against a letter. But if I didn't want to use parentheses, how else would I do that? So here's a quick little, we could go alpha W, alpha L, and then 0.5. And then divide by alpha P. See how I didn't use any parentheses? The more stuff that you have on top, the second you do a division, you can only do divide by 1. So this is one way to do it. Or you could do this. So that's without parentheses. And, I'll definitely make a separate tutorial on this. But you could do WL divided by P, alpha P, and then just divide by 2. You know what I mean? You're doing the multiplication first, and then you're dividing, and then you're dividing. So, because it's going to do PEMDAS in this order. It's going to come here and do W times L, and then it's going to divide by P. Cool, that's its own value. But guess what? Divide by 2. So this is another way to do it. And I'm just going to trust. That's a new one on me, so let's graph this out. And we're just going to do a window on this. What the hell are we even trying to get? We're trying to get X to be between 0 and 350. And our Y value will be this H. Because we could have H at 0, and we could have H at, I don't know, 200. I don't know, but let's graph it out and find out. Okay, hell yeah. So now window, let's get a value on this, 25, or a value at 200. So it says if X is 2, oh man, we need to trace this out. Okay, here we go, hell yeah. So what do we have here? Oh, it says this equation, this was interesting. We're setting this as our y value. You know what I mean? So this equation is a function of height. So we're going to go value 80. That was our height, and we get that 134. So cool. If our height is 0, so we're going to go zoom out. I think we just need to zoom this thing out. There we go. So we're going to throw an x value of 0. And if we threw in a height of 0, so let's go back to what this even shows. So we're saying if we put this at 0, and this thing only weighs 25 pounds, and we're only putting 18 newtons on it, well, yeah, again, just so what this is showing is if we put this as, this is 80, then the thing's going to be this way. But then we're saying, hey, where would we have to put the load? Well, it says we have to put the load at 400 millimeters. And I shouldn't have broke that one off the way I did it. I don't think I have any other good pictures. We toasted all of them. Because here it says x, so this equation that we put into our calculator says, hey, we're trying to find the value of x when h is 80. We did that and we got the right answer. But if h is 0, it says we have to put this load P at 400. This thing is only 350 millimeters. Oh, let's get our other pen. It says this thing is only 350 millimeters. And it's saying we would have to put that 18 Newton load way out here just to balance it. Because the discrepancy between these two springs was only 30 millimeters. And we're saying we have 80 up here. So in the initial, we were saying, hey, this comes down 30. But if we bring it up to 80, then it's 40 higher. So then this thing's the other direction. So just kind of using a graph to actually kind of figure out what's going on. So we're going to trace when this graph gets to 350. So there you go. So oh, and it's also when this height is at 16 millimeters, then we'd have to put the 18 Newton load all the way over here. You know what I mean? Cool, just to get this thing to balance out. And if the load is right in the middle, that means that the x would be, or the y value that we would want. So if we want to find the x when the load is in the middle. So when our value of x is at 350 divided by 2, which is 175. X is 175. Oh no, that didn't do it. Oh no, this is our x. That's why it's tripping me out. So now we actually have to do 175 and graph that line. So where this line intersects, so it's a quick way to find a y value. Oh man, another 10 minutes, then we'll finish it. Alright, hell yeah, my calculator is overheating, but what we were saying is if we put x at 175, that means the y value is 175. So how do you get a y value on a calculator? You just throw it in as a constant. So then you come up here and go to the intersect, first curve, second curve, and then guess. Booyah. So then we would have an h height of 67.9 millimeters. So at 68 millimeters, that is the height of putting these two springs where we could put the load right in the middle. Holy hell. Okay, so we are done with this problem, and we got an equation for it. And I don't know if you could simplify this equation. I mean, it's all just a bunch of constants through here, so those all look pretty... Well, everything's a constant. Everything's a variable. I just don't think you could combine variables. You know, on this one, you have the same thing where you could combine these as making the denominators the same. So it would be K1, K2 plus K2 divided by K2. So then you have similar denominators. So you can go K1 plus K2 divided by K2. And since you're dividing by it, you could easily just multiply by K2 divided by K1 plus K2. So that doesn't really help. That for me, that's not too exciting. And because you're still having this, even if you did that up here, you're still dividing by K1 plus K2, and there's nothing to factor out. And there's no K2s in the bottom anymore, so there's nothing to factor out there. Okay, hell yeah, I got to be done with this. But guess what? I'm going to try this one on a separate video. And, I mean, at some point, I just want to walk up to these problems, forget the numbers, and be like, oh, okay, so we have a K1, we have a K2, we have a length, 2, and it shows length 1 and length 2. And yeah, this is the final. And for me, walking up to this problem, I couldn't see that, hey, this length 2, at the end of the day, this length 2 was length final minus length initial. Like whatever the initial length of the spring was. So I would go here. I would go, and then to equilibrate these, I would go H plus, well, I still would. I would go H plus the initial length of spring 2 plus the change in length of spring 2. And then I would say that's going to be equal to length of spring 1 plus the change in length spring 1. That is 100%. But I just think it was harder to see that, hey, the length of spring 2, I mean, the way they have it drawn, they're saying that, hey, this length of spring 2 is the initial length plus the change in length. Now, if there was a force pushing up on this, you know what I mean? Because that could make the problem kind of interesting, where you have, 2 forces pushing up on these springs. Well, then you're going to have H plus the initial length of the spring plus the change in length. But the change in length would be negative. And then your L2 is the same thing. Well, it would be your initial length, let's say it was longer, plus the change in length. You know what I mean? So that would be a negative. So yeah, so I'm going to try this problem one more time and just see if I can intuitively get to here in under 10 minutes. You know what I mean? So that's what I'm going to try to do. Not try to explain every friggin' thing. And hell yeah. So that's going to be a separate video, but let's do it right now. And maybe I'll just tack it on to the end of this video. So let's throw 10 minutes on the clock and catch on the flip side. Alright, hell yeah. So we have material mechanics. Now this problem was a bummer because it involves springs and I was kind of getting everything wrong on it. So what I'm going to do is just with the wave of my hand kind of go through here. So I'm going to do a free body diagram. And this problem, I'm going to solve it without really, diving into what I'm doing or what's going on. Or just enough, you know what I mean? So every stroke of the hand, I'm going to be doing, something new. So we have a load here. Essentially, we want to make this horizontal. What we know is that, let's go to it. We know forces in the Y are the same. So F1 plus F2 is equal to P plus W. We got the force balance. We're going to take moments about this point. Positive moment there. F2, the total length, is going to be equal to W L over 2 is halfway, plus the load P times X. Now, this is a positive. Both those are negative, so we can equal. F1 and F2 are positive. Both these are negative, but they're equal. Cool. All right, but now we need a relationship with springs, and the first thing we need to know is like, whoa, what's going on here with the geometry? Geometry is king for all mechanical engineering problems. So we have, I'm going to start here. I'm going to say H plus the initial length of this spring. I'm going to call that L2 now, whatever the hell it would be, plus the change in length of that spring gets me to that point. Well, guess what? It's going to be horizontal at this point. So I'm going to start from the same datum and say that's going to be equal to the length of this spring, L1, the initial length, plus the change in length of spring 1. Cool. So now we have another equation. But now I need to know what the forces are. The forces right here and right there are just due to these springs. So I know the force of a spring is Kx. I say that's force K times change in length. So that's kind of what we're going to do. We're going to say F1 is spring constant 1, change in length 1. Well, cool. Don't we have a change in length there? Hell yeah, we do. And then we got F2 is equal to K2, change in length 2. Cool. Now, even like right now, we got 1, 2, 3, 4, 5 equations. Do we have enough? Because this was the king on this one. It involves this H. Sorry about the light. Let's get some new light in there. And hell yeah, we're 2.5 minutes in. So booyah. Let's count up our unknowns. 1, 2, 3, and then 4, 5. Is that it? 1, 2, 3 unknowns there. 4, 5 unknowns there. Oh yeah, there you go. So we got 1, 2, 3, 4, 5 unknowns and only 3 equations. But now we have the same unknowns. See how that pops up. So yeah, we got five unknowns, 5 equations. So let's get to it. I always know to work backwards with these. You know what I mean? So I'm going to throw. I want to get this equation with the forces. See how this is a force? So I'm going to say, hey, change in length 1 is F1 over K1. Change in length 2 is equal to F2 over K2. Now we can just get rid of these two. See how I can do that? So this equation is going to go H plus L2 naught plus F2 K2 is equal to L1 naught plus F1 K1. Cool. So now I combined all 3 of these equations. And I got this new equation. I'm just going to call it 3 prime because that reminds me that I used 3 and 4. Cool. So now I'm going to take this equation and now I got three equations left. So the smart thing to do is realize that this is the equation that has the x in it, where my load is going to be. I didn't even explain this problem. So it doesn't really matter. Well, no, it kind of does. But essentially, this spring is mounted way low, where its initial length is hella down here. So this thing naturally is resting like that. And then we have to put the load to balance it out. So even just doing that, if you can see that from the numbers, you know that the load has to be this side of halfway. So let's just guess. If this is 350, I'm just going to say the load is, let's say 100. That's what I'm kind of shooting for. Okay, now that's enough, and let's just solve the problem. Because that's the hardest thing, is just like, hey, how do you actually solve a 5-equation problem? Well, we're down to 3 equations. So now we just have 1, 2, and then this x is our third unknown. So this is the equation that we want to use last. This equation has F2 in it. So we want to make sure that this equation has F2. So we need to throw an F1 in. So we need to solve this equation for F1, throw it in here, solve that equation for F2, throw it in there. So yeah, it's a little bit headachy. So what I do is, I don't want to write very much. So I'm just going to say, hey, we have an equal sign here. Guess what? Now we have an equal sign here and a minus sign there. You know what I mean? You can go back and see what I did. But and now we just multiply by K1. So I'm just going to do this and go K1. So now we have F1 as a function of F2, and I'm going to throw it in here. So I'm going to take all this now. I'm just going to say, hey, it is up there. And I'm going to go, booyah, there it is. Plus F2 is equal to P plus W. So hell yeah. So now I have this. So now I really have to kind of factor through this K1. So we have H, K1 plus L2 naught, K1 plus F2, K1, K2 minus L1 naught, K1. Everything's got a K1 plus F2 is equals to P plus W. Okay, so now I need to round up the F2s and get all these over. So even just like right now, I'm just going to be like, hell yeah. plus L1, oh, what the hell was that? L1 naught K1. And then I'm going to go minus L2 naught K1. And then I'm going to go minus HK1. Perfect. They're all over there. Everything else is F2. Visually, I can see it. F2 is K1, K2 plus 1. And then I'm just going to divide all that by K1, K2 plus 1. Cool. So let's write this out. Maybe on a new sheet of paper, but maybe just right here. And so we have F2 is equal to, well, P plus W plus L1 naught, K1 minus L2 naught, K1 minus HK1 divided by K1, K2 plus 1. But yeah, we definitely need a new sheet of paper. So let's get that written up here, and we got F2. Well, we gotta. I'm just gonna totally do this now. We're trying to make faster videos, even if it's sloppy. All right, so hell yeah. So here's our equation that we wanted in, and we need to throw it into this one. So there's our F2. So we're going to take that whole thing and then multiply it by L. Cool, I think we can just do that. Just go multiply by L. And then once we got multiplied by L, that thing's going to equal WL. Well, we can subtract that. Minus WL over 2. That whole thing's going to equal PX. And then we can just divide by P. And then we got equation for X. So booyah. X is equal to P plus W plus L1 naught K1 minus L2 naught K1 minus HK1. L times P, multiplied this out, divided by K1, K2 plus 1, and then subtract WL2P, and there you go. So there's our equation for X, and that's within 10 minutes, but that's the one that I spent about 3 hours on. I threw it into my calculator. We can even do that. I have alpha P plus alpha W plus L1 plus K minus L2 K minus X for the H, and then K, alpha L divided by alpha P, and divided by K divided by J plus 1, minus alpha W alpha L divided by 2 alpha P. Graph that sucker, and we're going to throw in H at 80, so I'm going to go alpha value 80, and I get my answer at 134. Now, I only have 20 seconds, so you could throw this in. The problem said load 18 plus 25. This initial length was 250. 0.3 for here. I'm not using meters, but anyway. And that's it. I'm done with this video. Thanks for joining me. That's a video.